Oh, okay. I believe I am now live. So yeah. Hello and welcome back to today's life work where today we're going to be talking about ideal gas. And so yeah, before we just get started. Oh wait, no, actually let's just actually go ahead and just get started. We use an okay. Let's just go and just dive straight into it. We use an ideal gas that boil. Oh, something happened. Yeah, some something weird just happened. Huh. So yeah, let me just delete that first. Plug in the new one. We use an ideal gas that boil. Gay-Lussac thinks has six properties. Name and explain to the six properties. Ooh, okay. This is the first problem, huh? Hmm. Well, yes. According to my knowledge, no, wait, no. The ideal gas things has six properties. Um. So yeah, the first thing, according to my intuition, would be volume. Oh wait, no. Let's see. Uh. Like yeah, the first thing according to my intuition is volume, and then we got temperature, we got kinetics, we also got a pressure. Uh, hmm. What else? Hmm. The boil gay Lussac. Um. Wait. First, let me just manage this first. Ha, let me just. Oh, I need to do something first. Wait. Okay, I don't really know, actually. Mm, oh yeah, there could also be like the number of particles. Oh, energy. Energy could be something else. Um, what else? Uh, let me just check because of my conceptual problems are the worst. Let's see. Oh, yeah, the IMF, the intermolecular force. That that should have something to do. Um, things has six properties. Um, it might be correct, but yeah, I need to check first, just in case that yeah, I just made my first question literally wrong on the conceptual problem. So yeah. Um, pressure, volume, temperature. No. Oh. Oh. Oh yeah. So yeah. Actually, like yeah, there there is no IMF. Instead, that yeah, you have like the mass, which I don't think that it should actually matter. Well, I think it does. And then the Avogadro's number because of the thing, you know. No wait, no. Why do I write that as Avogadro's? It should be the gas constant. There we go. So those are the six properties. I believe so. So yeah, we can just jump straight to problem two. Okay. Let's just go ahead and just go to the second problem. Um, there are okay. There are several terms that need to be understood. Please look for the meaning of the following terms: isothermal, isobaric, and isochoric. Okay, so yeah, basically, according to my knowledge, iso means the same. So that means that isothermal would be um, this, it would be the same. Yeah, it would be the same temperature. Yeah, yep. This thing would mean that the temperature is constant. T is constant. Isobaric, I believe that it is it is on pressure because of bar. Let's see. Isobaric. Yeah, constant pressure. P is constant. And then lastly, isochoric, which I don't understand. Where does it where where does it come from? Isobaric. Um, I don't know, like, how do you actually just to spell this? I believe it's like that. Isothermal, and also isochoric. There we go. Which is the volume is constant. The V is constant. Okay. So with such, we have solved all of those problems pretty quickly. Yeah. So yeah, basically iso literally means the same. So let's go to number 3. An an ideal number of gases initially have a pressure of P and a volume of V if the gas undergoes an isothermal process. So, oh wait, what? So that the pressure becomes 4 times the original pressure, then the volume of the gas changes to, okay, so yeah, basically this means that the temperature would be the same, and then we know that actually the most general law would be PV equals to nRT. But then yeah, the T is constant, the N is constant, the R is constant, which means that PV equals to a constant. That would mean that, yeah, this would be one of the laws, which is Boyle's law, which is PV1, P1, V1 equals to P2, V2. And so, if the pressure becomes 4 times the original pressure, that means the gas would be a quarter of the volume. That's basically the logic. Because like yeah, P1 V1 equals to P2 V2. But yeah, P1 is P, V1 is V. That means that if P2 is 4P, that would mean that the V would be V over 4. Simple idea. Number 4. In a closed vessel, there is a gas that has a pressure of 2 atmosphere and a volume of 1 liter. If the gas pressure becomes 4 atmospheres, then the volume of the gas becomes, okay, we will just assume that the temperature is constant. This would mean that this would be the same Boyle's law, which is P times V equals to P times V. But yeah, we know that 2 atmosphere times 1 liter would equal to 4 atmosphere times a number, which would be half a liter. And that's the answer, half a liter. There we go. Because we are just using Boyle's law. Pretty simple. Number 5. It is known that a gas has an initial volume of V with a final volume of 4V. Meanwhile, the gas has a temperature of T. What is the final temperature of the gas. Well, this is the same thing, but yeah, instead this is isobaric because the P is constant. We can we can assume such. That means that this would be Charles' law, which is V over T would equal to V over T, which would be a constant. Therefore, therefore that the V over T here would be, so yeah, V over T, and then 4V over a number. But yeah, the goal is to get of V over T. And that means that, yeah, the T would be 4 times T. And yeah, that's the answer because that's the final one. Yeah, it's 4V divided by 4T would equal to V over T, which is true. So number 6. In a closed vessel, there is a gas that has a volume of 2 liters and a temperature of 27 degrees Celsius. If the volume of gas becomes 3 liter, then the gas temperature becomes something. Okay. So here is something critical, okay? V1 would be obviously 2 liters. V2 would be 3 liters. That's simple. But the temperature is 27 degrees Celsius. But we are not done yet because this is still at Celsius. And obviously, we are physicists. We love Kelvin. So that's why we just need to add it up by 273.15 for me. That would be 300.15 Kelvin. And so, we just need to go ahead and just calculate them all. I will just pull out my calculator, my scientific calculator. And yeah, because this is the same isobaric thing, so yeah. 2 divided by 300.15 Kelvin divided by 3. That should, no. I don't think so. Yeah. Yeah, because the T is still at the bottom, so yeah. That means it's 3 divided by D. Okay. So 3 divided by the answer that you got. Which means that the temperature would be, this is T1, this is now T2. This would be 450.225. You take the answer. What? You take the answer and then you subtract the thing by 273.15 to get yourself into the Celsius. Kelvin would equal to 177.075 degrees Celsius. Oh. Degrees Celsius. There we go. That is a very hot stuff, I should say. So yeah. Let's go to the next one. Number 7. It is known that a gas has an initial pressure of a certain amount of P, while its initial temperature is T. This means that it's isochoric. Later, the gas undergoes a change in pressure to 6P. What is the temperature of the gas now? Logically, you can actually just do a bit of the maths. Yeah, because this is isochoric, that means that we are going to be using Gay-Lussac's law. There we go. Gay-Lussac's law states that it's P over T would equal to a constant. So that means that P over T would equal to 6P over T. So we know that the answer would be 6P, no 6T. Logically correct. Number 8. It is known that a gas with a constant volume has an initial pressure of 2 atmosphere and the final pressure is 4 atmosphere. Meanwhile, the final temperature of the gas is 30 degrees Celsius. It's still at degrees Celsius. So yeah, we need to be careful about this. What is the initial temperature of the gas? Okay. The first thing that I see is that this guy is isochoric, and 2 divided by a temperature would equal to 4 divided by 303.15. So what? So yeah, this is Gay-Lussac's law, which would mean that it's 2 divided by by the P 4 over the temperature, which is 300.15 Kelvin. That means that I would get 150.75 Kelvin, which would equal to, wait, what? The volume is the same. The pressure increases. That doesn't make sense. Because it doesn't really make sense. 2 over T would equal to 4 over 20.15. Well, yeah, it is just like 2 times below that, so yeah. Logically, that's correct. Subtract the thing by 273.15, which would equal to negative 123.075 degrees Celsius. That is a very low number. So yeah, I guess that's the solution. Number 9. And number 9 is the final problem, because we are just doing this a bit more quickly than I expected. Oh well, how long has 24 minutes? Yeah, it's fine. So yeah, number 9, the final problem. An ideal gas of 2 liter has a pressure of 3 atmospheres with a temperature of 27 degrees Celsius. Determine the pressure if the temperature changes to 47 degrees Celsius and the volume to 1.6. So yeah, this is basically PV over T would equal to PV over T. That is the simplest way to write things down. This would mean that what so yeah, what we're now trying to find is the T2. No, the P2. P2 would equal to P1 times V1 times T2 divided by T1 and V2. Well, yeah, that is basically algebra. And so all you need to do is to just plug the entire numbers into your formula. No, into your calculator. So yeah, 3 atmospheres, multiply that by V1, 2 liters, multiply that by T2, which in this case is 273 plus 47. That's 100 and no, that's 330. Wait, what? 273. No, it's 220. It's 320.15 divided by T1, which in this case would be 300.15. Multiply that by the V2, which in this case would be 1.6. What you'll get is that the P2 would be around 4 atmosphere. And that's the solution. Oh wow, that's quick. Okay. So I guess that's the very quick life work of 30 minutes. I guess that's the record. So yeah. So yeah, I'm so sorry if this life work is much more shorter than expected. But yeah, thank you very much for watching this. And I'll just